Hello. This video is about other data structures that we're not going to cover in detail except for the Huffman Tree Lab. And this course has been about data structures, of course, from the start to the finish. And so we want to make sure you understand that there are a lot of data structures that we haven't covered. Here's a short list of some of the data structures. We're going to go to Huffman Trees and explain them, but the other, if you have time to review these other data structures, please do. So let's talk about Huffman trees. Huffman encoding is a way to compress a file, basically. It is using lossless data compression, and we created a tree you see here, and then we correlate it with a table. And then we use the code for each letter to encode any message that has been constructed from the Huffman tree that has it that is the input. Any letters can be used to encode it, but of course you can't encode a string without those letters. So how do you build it? Well, fairly straightforward. The first step is to compute the frequency of each character that you wish to encode. So you have a string, and let's say that we had 5 letters, A, B, C, D, and E, and they had frequencies of 3 for the A, 3 for the B, 1 for the C, 1 for the D, and 2 for the E. So we create a leaf node that has the frequency and the character, and put them in a priority queue so that the characters with lower frequencies appear first. And I would add that when there are ties, it's typical to put them in alphabetic order. So here you see C and D both have a frequency of 1. D comes after C. So we construct this priority queue, and then we take the 2 smallest frequencies, combining together. 1 plus 1 equals 2. Mrs. Jones would be proud of me. And we create a new node, insert that node at the end of the frequencies that start with 2, and then go on. So now the next step is to put 2 plus 2 together and get 4. Put that at the end of the tree of the string, like this. So 2 plus 2 is equal to 4. We carry along the characters in the first time we did it, because we want to construct a tree eventually. So we put 4 at the end of the 3s, and then we do that again with 3 plus 3 is 6. Put that in at the end after 4, and then 4 plus 6 is 10. So this is our final Huffman tree. Now how do we derive codes? Well, it's a lot like the Morse code project. We assign a 0 to the left branch and a 1 to each right branch. So, for example, E is 0, 0. C is 0, 1, 0, and so forth. So the next step is to build a tree, build a table that corresponds to each of those derivations of the letters. So here we have the table that corresponds to this tree. You see that B is 1, 1. A is 1, 0. E is 0, 0. So we can figure out the text. We don't need the frequencies anymore, but we often record them in the table. And basically, this is lossless compression. It's very interesting that there's no way we can go wrong if we follow this sequence. So 1, 0 corresponds to A, and then 1, 1 corresponds to B, 0, 0 corresponds to E, and so forth. So the idea that it's lossless means that we don't lose any information. And in addition, the way I like to think of it is that there is no way you can go wrong as you encode or decode a string. Now, why is this good for compression, for zipping a file, for compressing a file? Well, first of all, you can use the ones and the zeros as individual bits. You don't have to use the ASCII character for 1. You can use an individual bit, which is basically one bit of data. Secondly, the letters, and you don't see it so much in this table, but in a minute we'll show you the whole alphabet. In this table, the letters that occur more frequently have fewer digits, have fewer bits, and so it's basically the best you can do. So here's an example for the string better tree. So here, first step is we count the frequencies. B has a frequency of 1. E has a frequency of 4. T of 3, and so forth. And then secondly, we build a coding tree. Build a tree. By inserting characters into a priority queue with lower frequency first. Now notice we have a space also. Don't forget the space or else you won't be able to encode the space. So consider the space as just one of the characters. So we nominally put the space to the end, or it could come to the beginning. You'll have to look in the lab or the test to see where the space goes. Is it at the end of the alphabetizing or the beginning? So we build this coding tree, and just like we did on the previous slide, we remove the first 2 characters, B in space, and create a new node that's 1 + 1 in size, put it at the end of the frequencies that match it. So it goes after the R2, and insert the node. So that's what we do. And repeat until there's a single tree. So there's our tree. That's the end of step 2. Step 3 is to encode each character by its position in the tree. So we go down 0, 1 once and twice to R, 0, 1, 0 is B, and so forth. And out of that, we can construct a table. And then if we had this string beat read, whatever that means, it doesn't mean anything. You could build a string out of that table. B is 0, 1, 0. E is 1, 1. Here's another E, 1, 1. Then we go to 1, 0. That's T. Then the space is 0, 1, 1. And then an R is 0, 0. And then an E is 1, 1. Another E is 1, 1. And the final one, T, is 1, 0. So you decode left to right. So here's the example. 0, 1, 0 is B. Just like I walked through. Now, the English alphabet, this is an interesting diagram, and it shows if you encoded the whole English alphabet, you would see the fact that E has 3 characters, X has whatever that is, 2, 4, 6, 8, 9 characters, and so does J. All of these are low frequency characters. So then we translate that into a coding chart, and we see that E has 3, T has 3 characters, and now you can see why this allows you to zip a file, compress a file, because you don't use X that much. It turns out there are, at least according to Wikipedia, there are 127 instances of E in a typical English paragraph or book, whatever. There are 127 instances of E for every 1 instance of Q and Z. X is a little more frequent, and so is J, but not enough to make a difference. So that demonstrates how you can use a Huffman tree, how you build a Huffman tree, and how you can use it to compress a file.